Let's begin our study of nonparametric statistics with an introduction. I'm going to break this introduction into 3 parts. In this first part, we're going to examine what we learned in our first statistics course and see what is both good about that and where some problems might occur that we may be able to fix with nonparametric statistics. So what do we learn in Statistics 101, our very first statistics course? First, we assume that we have a representative sample of observations. That is, we can collect data on units that come from a population, but we only have available to us that sample, and that sample should represent that population. We also assume that we can make these observations so that every observation is independent of the other observations. That is, we are not influencing what we observe with one unit by what we observe with another unit. Now, when we make these observations, we assume that what we're observing can be put into a quantity from a continuous distribution. That is, we can quantify some underlying construct. And then we say one of 2 things about these quantities. Either that they are from a distribution that has a normal shape, that is, a normal distribution, or if we don't know that the distribution is normal, we have a large enough sample size, because with a large enough sample size, we can rely on the central limit theorem. We then start by looking at the major features of the data through visual analysis or a graph of our scores. We don't worry about the specifics at first, but rather we want to get an overview of the shape of the data and various characteristics of the data. Then we drill down and get more specifics, finding these statistical indices of various characteristics of the data, such as the mean for the center of our distribution, the standard deviation for the variability of the distribution, and other statistics. Now, these statistics serve 2 purposes. First, they're descriptions for our sample, but also they're estimates of the population parameters that we will never be able to observe. We then can use the sampling distribution. Remember that a sampling distribution is a distribution of a statistic that we can theoretically obtain as if we had collected multiple samples from our population and then computed the statistic for each one, the result being the sampling distribution. We can use that sampling distribution to construct a confidence interval. And most commonly in Statistics 101, that's a confidence interval for the mean or the center of the distribution. This interval then bounds the population mean with a known degree of certainty. This is, in a nutshell, the main points that we learn in a first statistics course. Now, hopefully in your first statistics course, you also talked a little bit about design, measurement, and analysis, although really analysis is the only part that is statistical. A research design is a blueprint for making observations. The first 2 steps that we took in Statistics 101 really is part of the design rather than statistical analysis. That is, assuming that we have a representative sample of observations and assuming that each observation is independent of every other observation. Typically in statistics courses, we don't spend much time talking about something that is extremely important, and that is measurement. Measurement is the method of observation to yield data. In Statistics 101, the instructor usually supplies data, and there is very little discussion about whether these data are actually representative of the constructs that we are interested in. The assumption of quantitative data is based on measurement that yields such data. Creating and calibrating or scaling instruments is part of the measurement process. And without this going on behind the scenes or prior to us doing our analysis our analysis is probably going to be worthless. Then that analysis is the process of understanding and making sense of data. Statistical analysis includes graphing, descriptive statistics, and making inferences. And valid statistical analysis requires understanding both the design and measurement. And what I fear is this is lost in many Statistics 101 courses where we just assume we have a good design and we have good measures, and don't talk much about the fact that if we don't have either of these, then all we're doing is spinning our wheels and doing something that may look very sophisticated, but doesn't really lead to conclusions that match reality. This suggests that in Statistics 101 there may be some problems. We assume that observations are quantities from a continuous distribution. To treat social and behavioral responses as interval measurements, we have to use well-developed and carefully calibrated instruments. We cannot simply just make up scores in a willy-nilly fashion. We have to go through the science of measurement. That in itself could involve learning in one or more measurement courses in order to get a start in knowing how to have a well-developed and carefully calibrated instrument. Further, many social and behavioral observations are not quantities, but rather are categories, either unordered, what we can call nominal data, or ordered categories that we can call ordinal data. Yet little play is typically given in Statistics 101 to the fact that we may have categorical data. We assume that the observations are quantities from a continuous distribution, but the underlying distributions of social and behavioral observations are often not continuous, but only imagined as theoretically continuous. And in practice, they are never continuous. In order to have continuous data, we would have to measure with infinite precision, which obviously we never can do. So our measures are always discrete. There are some additional problems. We say we know that the underlying distribution is normal. Most of the time, we don't know this. Social and behavioral response data typically do not follow a normal distribution unless the measuring instrument has been calibrated to provide normally distributed data. Well, how often is that done? In a 1989 article by Ted Masseri from the University of South Florida entitled "The Unicorn, the Normal Curve, and Other Improbable Creatures," he discussed his investigation of the distributional characteristics of 440 large sample achievement and psychometric measures and found that they were all non-normal. Not most, not a few, all of them were non-normal. Furthermore, he looked at the tenets of normality-assuming statistics, and those appeared what he called fallacious for these commonly used types of data, leading to the conclusion that a reevaluation of statistical robustness literature appears appropriate. In short, his findings showed that what we typically assume in behavioral and social statistics courses, that is, that the data are normally distributed, just is not the case. So how do we get around that in Statistics 101? We say if we don't know the distribution is normal, but our sample size is large, we can invoke the central limit theorem. And indeed, the central limit theorem is powerful and forms the foundation for much of what we do in parametric statistics courses. The rule that is used in many textbooks, that n be at least 30, or sometimes you'll see n at least 50, is based on a unimodal distribution with very little skew, so that larger sample sizes are needed for bumpy or higher skewed distributions. And then there is the fine print that we never talk about in Statistics 101, and that is The central limit theorem does not work for all distributions. There are some kinds of distributions, such as the Cauchy distribution, in which we will never achieve a normal distribution no matter how large our sample size. So unless we're dealing with some clean kinds of distributions and those without much skew, we really cannot rely on the central limit theorem to pave the way for us to do regular parametric statistical analysis that we learn in Statistics 101. Procedures that are based on the normal distribution are the most powerful procedures when the underlying distribution is normal and the central limit theorem does not need to be invoked. That is important to know, because often what you'll hear people say is that procedures based on the normal distribution are the most powerful, period. And they don't realize or forget that that's only true if the underlying distribution is normal. And in fact, even if the central limit theorem will work, that still doesn't make those procedures the most powerful. We would like analytic tools that accomplish the following. They are appropriate for our actual level of measurement, no matter what that level of measurement is. So we do not want to treat data as continuous or quantitative that are not quantitative. And when data are categorical, if there is an order to our categories, we want to take advantage of that order and not treat it as though it were unordered categorical. And then if it is unordered categorical, we want to do the best possible thing we can with that data. That is, what we want to do that goes beyond Statistics 101 is identify the actual level of measurement and then use the procedures that will provide us the most power and the most information for that level of measurement. We want to take into consideration that there is a discrete nature to our data, even if we assume that the underlying construct is theoretically continuous, there is still a discreteness to our measures, and we want to involve that in our analysis. We want to use data from any kind of distribution, not just assuming that we have either a normal distribution or that we can invoke the central limit theorem. And we want to be able to do this with any sample size. If we need to invoke the central limit theorem with a large sample size, what about if we don't have a large sample size? We want to avoid that problem. And then we want to provide the most powerful inference we possibly can. And if we know the level of our measurement, and if we take into account the discrete nature of our data, and if we are not sure that the underlying distribution is normal, then there are methods that are actually going to provide more power than we would get if we were to do what we learned in Statistics 101.